Welcome to Spring LIB.
Okay, which of the following compounds are chiral? Great. So what do we need for chirality? We need a carbon that is bound to 4 unique things. This is a CH3, this is a CH2, right? So CH3 has 3 non-unique things. A CH2 has 2 non-unique things, right? It can't be chiral. No CH2 or CH3 is capable of being chiral. So we can kind of just go through and identify those. No CH2. Well, what about here? We've got, we don't have a CH2 or anything like that. We've got a hydrogen, then a bond to something with an oxygen on it. Oh, but here's the issue. This bond to the rest of the chain and this bond to the rest of the chain are both identical. This is an ethyl group and this is an ethyl group. So in that case, that carbon is not chiral. For the remainder of the molecule, we've got a CH2, CH2, and a CH3. So that's not going to fly. That's not chiral. Okay, let's continue. Oh, my pen freaked out there. Okay. And NH2 and HO. Okay. So just continuing on, this is a CH2, so that's no good. What about here? Well, unshown is a wedge to hydrogen. So I see this bond to the carbonyl being very different than this bond to the carbon with the oxygen on it. So that's unique. And then the other two are a nitrogen and a hydrogen. Yeah, that looks chiral to me. We've got a carbon with 4 unique substituents. All right, continuing onward. Bromine here. Unpictured is a dash to a hydrogen and a double bond there. Okay, well, first we can just dismiss all the CH2s. No good, no good. If we're interested in chirality, then that means we're not really interested in double bonds or sp2 hybridized carbons. But all right, we've got 1 carbon left, and the question is, like, clearly the bromine and the hydrogen are unique from each other, but is this bond to the sp2 hybridized carbon up here unique from this bond to an sp3 hybridized carbon, right? And the answer is yes. The way we can formally determine this is calculate what's everything that that carbon is bound to. It's bound to a carbon, right? But it's also bound to 2 hydrogens. So I can say carbon, carbon, hydrogen, right? What about this carbon here? Well, it's bound to a carbon, but it's like doubly bound to that carbon and a hydrogen. So unless these are exactly the same, if the connectivity of this upper carbon is this exact same as the connectivity of this lower carbon, then they're not the same bond. So the green bond is very different from the blue bond. Therefore, there are 4 unique substituents here, and this is chiral. Okay, let's continue. So far, 2 and 3 are chiral. Oh, this one's tricky, right? So it looks like it could be chiral, and I'll explain why, right? We've got a bond to a hydrogen here, and this bond to a hydrogen here. The issue is, yes, there are 2 carbons that each have 4 unique substituents, which is, that's necessary to be chiral, but there's one other thing we can look for to determine if something's chiral or not, and that is an internal mirror plane, right? So if the molecule contains an internal mirror plane of symmetry, then it cannot be chiral. So one example would be the following. Right, this looks like it could be chiral, but because it contains an internal mirror plane, it is not. This molecule is the same, and it's not easy to see, but if we rotate about this bond, we can end up with the following picture that is exactly the same molecule. And then hopefully now it might be easy to see how we can split sort of in between the chlorine and the hydrogen and make a plane about which the molecule is. So you kind of think if we want to look down that plane, we're going to end up with a carbon towards us, hydrogen up and to the left, and chlorine up and to the right. And in the back, there's going to be another carbon that looks exactly the same. So we're saying down that plane, it's got an internal mirror plane of symmetry. So it's not chiral. So it's just 2 and 3, which is option 2.